Hello. In the last two lessons, we discussed the crust of the earth and the interior of the earth. In today's lesson, we will see the surface of the earth. Now, I'm sure you remember we talked about the dynamic nature of the earth. Everything on the surface, on the crust, and the interior of the earth is changing. That means the surface of the earth must be an ever-changing surface. The earth's surface does not exist in a static, unchanging, natural condition, and it is always interrupted by the work of humans, but instead it is a dynamic system of which humans is a part. Now, very often we say, well, humans destroy the surface of the earth. Well, the influence of humans on the surface of the earth is very minimal. The natural conditions is what shapes the surface of the earth. So the earth's surface does not exist in a static, unchanging natural condition interrupted only by the work of the humans, but it is a dynamic system of which we are a part. Now that means knowledge about the changes to the earth's surface and the underlying processes that induce them has enormous impact on how society responds to these changes and ultimately the cost of responding to change. For example, we live on the surface of the earth that is prone to earthquake, mudslides, all kinds of natural phenomena, hurricanes, all these. Now, once you know what we expect, so knowledge about the changes of the earth's surface and the underlying process that induce them. What are some of the underlying processes? We will talk about that. Then the society can then respond to these changes. Now, human beings are very good at responding to disasters, aren't we? And that is the reason why our civilization thrives. We know how to respond and adapt to changes. Well, within a certain limit. Well, it is important that we understand the past and present environments and the geological, biological, and hydrological geochemical processes involved in the environmental change so that future environmental changes and impacts can be anticipated. See, in order to anticipate what is coming to the future, we need to understand what has been happening in the past, because the picture of the past is actually a picture of the future. The future can be understood by understanding the future can be understood by understanding the past. Well, geological changes take place slowly. The changes that take place on the surface of the earth and everywhere on the earth are so slow that our lifetime is actually very slow to know about it and respond to it. Is that right? That the changes that occur in mountains, canyons, and shorelines are difficult for a person to see. I asked you yesterday, if you come back 50,000 years from now, will you recognize some of the features of the earth? Well, it would have changed. Mountains will change, the valleys will change, the canyons will change, the plateaus will change, rivers will change, shorelines will change, islands will change, Florida might be underwater. You see? So much changes can happen, but changes do happen very slowly. The internal and surface dynamics cause continuous evolution of the Earth's surface. Now, some of the changes that we talked about in the last two classes are occurring continuously, and that causes the features of the surface to change. The surface of the earth is in a continuous process of change. Now, most of the evolution of the earth's surface is due to orderly change with time and the ongoing work of water and other forces of nature. You see, the two important things that shape the surface of the earth are caused by water and wind. We call it erosion. And then the forces of nature, which we actually talked about, the motion, the plate tectonics. And we will be looking at both these forces today in some detail. Now, this is often referred to as the principle of uniformity. Now, what does the principle of uniformity says? The changes on the Earth's surface have been taking place in an orderly manner. It means there's some predictability about it in an ongoing manner. That means if you understand what has been happening for the past 200 years, you probably will have an understanding of what will happen in the next 200 years. But remember, in a geological scale, 400 years is a very short time. So I would say, if you can understand what has been happening in the last 1 million years, probably we have enough understanding then to predict what is likely to happen. So what is the principle of uniformity? The principle states that the present is the key to the past. What has happened in the past? The present is the key to the past. What is happening now may be a key to understanding the past. So what has happened in the past is an indication of what is happening now and what will happen later on. So the principle of uniformity is an important principle. Once we are able to understand it, we are able to predict some of the things that could happen. Now, the rates of operation may or may not have been the same in the past. Some events would have happened more slowly or more quickly, but the events you see occurring today are the same events that occurred in the past. So the events do not really change much. Sometimes it may speed up, sometimes it may slow down, but what events you see today are events that occurred a long time ago as well. And those are the events that shape the surface of the earth. Most of the earth's surface, that is 70%, is actually covered with water. Is that right? Everybody knows that. And the remaining 30% is taken up by the 7 continental land masses. Now, underneath the water that fills the oceans and the dirt and the plants that cover the continents, the Earth's surface layer is made of rock. We talked about that in the last lesson. The Earth's surface is actually a big layer of rock and is broken into pieces. We call it tectonic plates. Well, and over the rock you have oceans, and of course you have dirt and mud that forms the soil that is very important for our civilization. We are able to build houses, we are able to grow crops, is that right? Because the soil, and all that is part of the rock system that makes up the surface of the earth. This outer layer formed a hard, rocky crust. As the lava at the surface cooled 4.5 billion years ago. Now the crust is broken into many large plates that move very slowly relative to each other. We talked about that in the last class, and we're going to build it up today. Now the mountain ranges form when two plates collide and their edges are forced up. You see, one way to form mountains. Many other surface features are the result of these moving plates. So today we will look at many of these changes. In fact, we looked at many of these changes in the last lesson. what happened when these plates moved towards each other, didn't we? We talked about what happens when continental plates and oceanic plates converge. What happens when continental plates converge to a continental plate? In fact, all these surface features are the result of the movement of these plates against each other or sliding each other and so on. Now, therefore, what are the processes that build up the surface? As I told you earlier, there are two main phenomena that build up the surface, that keep the surface in a constant state of change. What are they? One is the erosion caused by rain and wind. The second is the movement of the tectonic plates. Let's talk about erosion first. Now, erosion happens when running water, sea waves, wind, glaciers, and so on pick up materials from the Earth's surface and carry them to other locations. You see, this is a process that is continuously happening. The Earth's surface gets broken down due to wind and rain, and the debris is continuously being carried from one place to another. The actions of erosion and deposition, is that right? Carrying away the debris and depositing it in some other region. So we call it the actions of erosion and deposition work together after existing landforms and create new ones. Is that right? Now, deposition occurs when silt, sand, and other materials are carried by flowing water and deposited in places on the surface of the earth. We see examples of that in many, many places on the surface of the earth. Now, gravitational pull plays a major role in the process of erosion and can cause huge amounts of soil or rock debris to be carried down a slope, such as the case of a mudslide. Even today, there was news about a great big mudslide. Was it in San Diego? Yes, I think so. Great big mudslide in San Diego which destroyed 7 houses, moved huge amount of the surface of the earth from one place to another. Look at the way the natural forces change the surface of the earth. Now, this occurrence is referred to as mass movement. A large mass of the earth's surface is moved from one place to another. In another type of mass movement, certain areas of the earth's surface are pulled by gravity and sink below the ground level. Have you seen such things happen? Sinkholes. All of a sudden, sometimes you see the middle of a road sank and became kind of a well. Well, when you have soft spots, gravity pulls materials downward, creating this process. Now, gravity also naturally pulls rivers and streams down. Now, what is the reason for the flow of rivers? The rivers and streams flow because of gravity. You can see most of this erosional process is actually helped by the gravitational force. Now, all of the rocks and minerals that a stream carries are called the load of that stream or the load of that river. You see, as the rainwater flows into streams and streams empty into rivers, the load they carry, that is all the debris they carry, get deposited in each place as they flow. Little streams pass their loads along to bigger ones, and bigger streams pass their loads along to rivers, and ultimately most of it will end up on the seabed. When the sediment contained in these loads is deposited at the mouth of a river, a delta or a low-lying plain is formed. If you go down to a place where a river joins with the sea, you can see the example of this delta. The river will be carrying a whole lot of this load, and just before the river water joins with the sea, you can see all these sediments gets deposited. You get a delta formed. Now, this is a good example of a river delta. Now, sometimes the sand, clay, and silt sediments from these fan-shaped deltas, the delta is like a fan-shaped because the water, as it splits into many pieces and maybe joining with the sea, all these areas will have the deposits built up there. So these fan-shaped deltas are picked up and dropped on the surrounding land areas. Now, when there is a flood, all this debris can be picked up and dropped in the surrounding areas. In fact, this is one of the ways surrounding areas are made fertile for the cultivation of crops. Now, this is the reason why ancient civilizations flourished near riverbeds. Is that right? A lot of civilizations, Indus Valley civilization, most of the ancient civilizations were built around river valleys because the soil around the river valleys were fertile. You see, the debris and the nutrition that is carried from various parts were all deposited on the river deltas. And so civilizations flourished on the river deltas. In recent years, geologists have discovered that much of the world's petroleum resources are found in ancient deltaic regions. Well, that was a brief discussion on erosion, what erosion does to the surface. We will take it up once again. We will talk about water erosion and wind erosion one more time. But in this lesson, we're going to concentrate more on the second process. And what is that? It's the diastrophism, volcanism, and earthquakes. And we're going to talk about the effect of this process in the shaping of the surface of the earth. What is diastrophism, volcanism, and earthquakes? All these processes are brought about by the slow motion of the plates, the plate tectonics. So this is actually the study of plate tectonics. All the possible movements of the Earth's plates, including the drift towards or away from each other, and any processes that deform the Earth's surface are included in the study of diastrophism. So you can see diastrophism is, in a nutshell, plate tectonics. Now, it produces many of the basic structures on the Earth's surface, such as the plateaus, mountains, and falls in the crust. Diastrophism, volcanism, and earthquakes are closely related and caused by events involving plate tectonics. In fact, all these things can be put together and called one name, that is plate tectonics. Well, look at the nature of the Colorado Plateau. That is the result of the changes on the surface of the earth. And this is the Long Peak in Colorado. All different types of shapes on the surface of the earth are all due to these constant changes. Now, in order to understand plate tectonics, let's look at some important terms. The first important term we are going to look at is called stress and strain. What is stress? You see, if you apply a force, you can see a spring here, and if I apply a force on the spring by suspending this mass, we say the spring is subjected to a stress. Now, what is stress? A stress is a force and we define it as force per unit area. The spring is subjected to a force, and the force per unit area is what we call stress. And almost everything on the surface of the earth, especially the plates that make up the earth's crust, is subjected to tremendous force. So the movement of the tectonic plates produces forces that deform the earth's crust. So an understanding of this force is very important. These forces are greatest at the plate boundaries and can be transmitted throughout the plate. So when two plates come together like this, the forces are greatest at the boundaries because the plates will be trying to go past each other. Is that right? So those forces will be greatest at the boundaries and can be transmitted through the length and width of the plates. Now, what is stress? Stress is a force acting on a unit area, and we define stress like this. Stress equal to force divided by area. So, if there is a certain amount of force acting on this surface, now I can actually apply a force on it by placing the rock. Look at this. I'm going to place this rock on this surface. So there's a great force on that surface. If I divide the force by the area of the plane, so the total force acting on it divided by the area will give me a measure of the stress. So what is stress? Stress is force acting on a unit area, and you obtain that by the equation. Stress is force per unit area, force divided by area. Now we measure stress in a unit called Newton per meter squared. Force is measured in a unit called Newton, and area, you know, is measured in meter squared. Therefore stress, which is force per unit area, is measured as Newton per meter squared. Now what is strain then? Strain is a measure of the deformation or the change in shape. Now watch, when this spring is subjected to a stress, when I pull the spring by hanging this mass, you can see the weight of this mass is going to apply a force on the spring, and the spring is pulled. Now, did you see the spring has been deformed? You see, that's the original spring. When I leave the mass, you can see what it does to the spring. Now, this is what is called strain. In other words, the stress causes the strain. The strain is the deformation produced by the stress. All stresses produce a kind of deformation, and the deformation produced by a stress is called a strain. Strain is a measure of the deformation or change in shape of the material. Alright, I just talked about what the spring, what the weight hanging from the spring does to the spring. Now we classify type of deformation on a material experiences based on the relationship of stress and strain. Now what kind of relationship exists between stress and strain? If the strain is directly proportional to the stress. Now what does that mean? The strain is directly proportional. You know the meaning of direct proportion. If you say one quantity is directly proportional to the other, it means when one increases, the other also increases. You see, the amount of money you earn is directly proportional to the amount of time you work. The more time you work, the more money you earn. That's the direct proportion. Now look at the deformation, or look at the strain of the spring when I subject this to stress. Now as the stress increases, the strain, you see that? I subject it to a small stress. Now the strain is small. I increase the stress, the strain is increasing. Increase it further, there you are. So in this case, the strain is proportional to stress. As you increase the stress, the strain also increases. Now this kind of a deformation is called an elastic deformation. You see, in an elastic deformation, the most important part of the elastic deformation. Now watch what happens to the spring when I remove the stress. When the stress is removed, the spring came back to its original shape. Now this is elastic. If the spring loses shape, then the spring is not elastic. You see, in this case, when the deforming force is there, there is deformation. When the deforming force is removed, the spring goes back to its original shape. You can see, we say the spring is elastic. On the other hand, there are materials which, when subjected to an external deforming force, now look at this, I'm going to supply a deforming force on this. Now, when I'm going to apply deforming force, now watch what happened. When I remove the deforming force, can you see what happened? It did not get back to its original shape. Actually, this one just broke. Alright, so depending on what the stress does, the kind of relationship between stress and strain, we have different kinds of deformation. So what is elastic deformation? If the strain is directly proportional to the stress, and if after the stress is released, the material returns to its original shape, then that deformation is elastic. On the other hand, when the stress is removed, if the object does not regain its original shape, then the stress is called ductile. Now, let me see if I can show you a ductile deformation. Now, here I have an object. I'm going to subject this to a stress. Now, look, I'm applying it to a stress. Now, when I remove the stress, did the object go back to its original shape? No, it did not. So, this kind of a deformation, where when the deforming force is there, it deforms, but when the deforming force is removed, it does not go back to its shape. So this kind of a deformation is called a ductile deformation. So I have a ductile deformation and an elastic deformation. So you must understand the meaning of these well. A third type of deformation is brittle. If the stress causes the material to break. Now you remember what happened in the case of this material. You can see it is actually broken. You see, I can't use this again. I simply spoiled this piece of cork. When the deforming force is on, it causes the material to break. Such a deformation is called a brittle deformation. So once again, elastic deformation, ductile deformation, and brittle deformation. And why did we discuss all this? Because when rock materials are subjected to the deforming forces, a rock can undergo elastic deformation, ductile deformation, or brittle deformation. Now, when the force is removed, the rock can come back to its original shape. That will be elastic. When the force is removed, the rock can remain in the deformed state. That will be ductile. And when the force is applied, the rock can break. That is brittle deformation. Now, there are three types of stresses. Let's look at these stresses. The first one is called tensional stresses. That is when one part of the plate moves away and the other part do not. Now look at, if this is a piece of rock and if I pull it like this, can you see I'm pulling with the left hand to the left and the right hand to the left? These are tensional stresses. It pulls from either side. Now the second type of stress is called compressive stress. In other words, I have the same piece of rock, I can apply compressive stress. So distinguish between tensional stress and compressional stress. Now there is a third one called shear stress. Now what is a shear stress? Let me see if I can demonstrate that to you. You see a box. Let's see if I can demonstrate that on a book here. You see the book sitting here. I can apply a force on it so that I'm going to show it this side. Now look at the vertical side of this book when I apply a force on the top. What's happening there? Look at that. Now the vertical edge is now tilted. So the shear stress is produced when the two plates or two rocks slide past each other, and this is an example of a shear stress. It simply changes its shape. So in the case of rock, shear stress occurs when one rock piece or one plate slide past the other. So let me talk about that again. This is the shear stress and this is the compressional stress and this is the tensional stress. Alright, let's go on and look at more of those. And I have illustrated that here. Tensional stress, compressional stress and shear stress. Okay, a rock unit might respond to stress by changing in volume, shape or just by breaking. So we will look at what happens when a rock is subjected to these kind of different strain. In elastic strain, the rock will recover the original shape after the stress is removed, just like the spring recovers its original shape. In plastic strain, the rock is molded or bent under the stress. So under the stress, the rock will be deformed and it will stay like that. It's a plastic strain. And in a fracture strain, the rock will simply break into pieces. So you can see here, this is the undeformed block. Here you have a brittle deformation. The rock breaks into pieces. And here you have a ductile deformation. The rock simply got flattened out due to the stress. Alright. Rocks are better able to withstand compression rather than pulling apart. So rock pieces can withstand compressive forces more than tensional force. Tensional force tends to break rocks, whereas it can withstand more of compressional forces. Now, cold rocks are more likely to break than warm rock. I told you that in the last class. You keep a plastic sheet in your freezer, take it out after a week and give it a good bang, it will break. Whereas you heat a plastic sheet, you can mold it the way you want. You see that? Just like that, a cold piece of rock will be brittle, will break very easily. Whereas warm rocks which are underneath the ground, the rocks are very warm, it's hot. And hot rock can be molded into shape. When subjected to pressure, they can change their shape and undergo ductile deformation. Now, rocks at great depths are under great pressure and high temperature. That means they can undergo ductile deformation. So these rocks tend to undergo plastic deformation. Plastic deformation is the same as ductile deformation, and bend extensively. So there are many instances where great big pieces of rock, when I talk about the piece of rock, remember it is millions of square kilometers, big pieces of rock. Rocks at less depth have a lower elastic limit and break easily. They are cold, they will break very easily. Now, rock deformation often results in recognizable surface features. In fact, a lot of surface features that we see on the surface of the earth, like mountains, valleys, are all due to the deformation caused by the bending or the plastic deformation of rocks, and we call these features faults and faults. A fault is where two rocks have been interfering and produce deformation, and similarly a fold. So we're now going to look at some types of faults and faults. Well, these faults and faults are responsible for the features we see on the surface of the earth. You see all the elevated and depressed areas, big canyons and big high mountains. All these are features created by the folding and faulting of the rocks. If you look at this, the colors indicate the height. Now here, this is about 0. That means as you go on, these colors, the red colors indicate very high altitude. Now that means all these mountain regions, look at the Himalayas, they are very high altitude. These are the Andes, these are the western mountain ranges. All these are very high altitude, and as you go deeper into blue, they are say about 11,000 feet below the sea level. This is the sea level here. As you go deeper in the bluish areas, it's becoming deeper and deeper, and all these changes on the surface of the earth is actually caused by the folding and faulting of the rock pieces. So ocean trenches and ocean floor have the lowest elevations on the image and are colored dark blue, and elevation is indicated by color. Let's now talk about folding. A fold can be defined as the bend in a rock that is in response to compressional forces. So when you subject a rock to compressional forces, it tends to buckle and fold. So faults are most visible in rocks that contain layering. For example, I showed you in the last class the sedimentary rock. If you can see, this rock contains layering. That means when this kind of rock is folded, you can actually see the folding very well. Okay. Now here I have one type of folding. This kind of folding is called monoclinic. The simplest type of folding on a rock is called monoclinic. It's a simple folding. Alright? And this fold involves a slight bend in otherwise parallel layers of the rock. You can see this is a sedimentary rock with different layers. Originally it was a parallel layer, and when subjected to compressional stress, it underwent this folding. That's a monoclinic fold. Now, an example of a monoclinic fold is the Lake Victoria in Uganda. You can see that is a monoclinic. It's a rock that has folded to form a basin-like structure holding the water. Alright, the second type of fold. I want you to take note of the different types of folding that we're discussing. The first type is called the monoclinic. The second type of folding is called the anticline. This is a convex fold in the rock that resembles an arch-like fold. You see, that happens when you have a rock being compressed and it goes like this. You see, very simple. Compressional force causes the rock to go like that. That is an anticline. Now note how the rock layers that dip away from the center are symmetrical, because the forces were acting from either side. You can see a symmetrical fold is created. Alright. Now, this is the picture of an anticline. Look at the rock that is actually bent due to stresses. The picture is actually very clear on the formation of an anticline. And look at another example. This is the result of stresses from either side folding and raising the rock upward. Isn't that beautiful? Well, there are many structures on the surface of the earth. So this is folded and uplifted sedimentary rocks in Colorado Springs. Alright? The third type of folding is called the syncline. You see, syncline is the opposite of anticline. The forces that are the stresses, forces that are applied, well, bend it downward. The anticline produces the upward bend. Syncline produces the downward bend. So, syncline is a fold where the rock layers were wrapped downward. Both anticlines and synclines are the result of compressional stress. Compressional stress. Now here is an example of a syncline. Isn't that beautiful? Look at the layers that have been folded down. There's a beautiful representation of that. Note how the rock layers dip towards the center of the fold and are roughly symmetrical, aren't they? They're quite well symmetrical. And this is another example of a syncline. And that's a beautiful picture there. Now, syncline falls in bedrock near St. Goddard in Canada. And you can see that's a place where a lot of people go and visit. Sediments due to weathering tend to collect in the trenches of the synclines, filling them in. You can see actually the trenches here have been filled in. If it were not broken on the sides here, you will not know that there is a syncline underneath the ground. Alright. Now the San Joaquin Valley is a very large syncline in California. So some of the valleys that we see on the surface of the earth are actually folded rock. Alright, we talked about folding. Now let's talk about faulting. What is faulting? Extreme stress and pressure can sometimes cause the rocks to shear along a plane of weakness, creating a fault or a break. A fault is simply a break. Faults form in rocks when the stresses overcome the internal strength of the rock, resulting in a fracture. So the external pressure is so high that the internal forces cannot withstand it, and therefore the rock cracks. And faults occur from both tensional and compressional forces. That means faults can occur due to the tensional forces as well as compressional forces. And we will look at some of these as we go on. Many of these faults are in mountainous regions. Well, here I showed you this picture before where you have earthquake regions. You see, earthquake regions are good examples of faults, where faults are formed on the rock. So locations of some of the major faults on the surface of the earth, and most of it is found in the mountainous areas. Over here, about the Andes, about the Himalayas, all these are mountainous areas. The faults are named according to the type of stress that acts on the rock and by the nature of the movement of the rock blocks either side of the fault plane. So let's look at some of the names of different types of faults. The first is what is called the normal fault. A normal fault occurs when tensional force, pulling away forces, act in opposite directions and cause one slab of the rock to be displaced up and the other down. Now, this is an example of what happens in a tensional situation. This is a normal fault, and I think I have an animation here. Watch this. The forces are on either side. So the break occurs, which displaces one piece above and one piece below. And that is what normal fault is. A normal fault occurs due to tensional forces. Now, this is an example of a normal fault. Can you see how the rock has broken? One piece is pushed up, the other is pushed down. You see, the picture is more compelling when you see the layering there. This is a normal fault subjected to tensional force, resulting in the piece on the right moved up, the piece on the left moved down. The second type of fault is called the reverse fault. Keep track of these names. Normal fault due to tensional. Now, reverse fault is due to compression forces. Compression causes one block to be pushed up and one block to be pushed down, just the way the tension did in the previous case. Now, watch this. Now, compression forces from either side causes the rock to break so that one piece is pushed up and the other pushed down. And watch this, what happens? This is compressional stress, and that causes the reverse fault. So again, normal fault, and this is reverse fault. The compressional forces break the rock so that one piece moves down, the other moves up. And look at a convincing example of this. This is a reverse fault. The compression, you can see the clear effect of compression. It broke and this piece went down and almost underneath the other one. And this is a clearer effect of compression. And you can see the difference between normal fault and reverse fault. A third type of fault is called a Graben fault. Is produced when tensional stresses result in the subsidence of a block of rock. Let me show it to you. Now, such fault is actually results in the formation of rift valleys. Now, look what happened. The tensional forces result in a middle piece to break and it sinks. That is the Graben fault. And that is, you can see, a rift valley. A rift valley is formed as a result of a Graben fault. Alright? So, have you kept track of the types of faults? Normal fault, reverse fault, and Graben fault. A fourth type of fault is called a host fault. And it is the development of two reverse faults causing a block to rise up. And this is how plateaus are shaped. So this is the host fault. In other words, it is the opposite of the Graben fault. Is that right? The compressional forces cause the middle piece to break and rise up. Now, the final major type of fault is called a transform fault. And a transform fault occurs where the rock pieces slide past each other. You see, the two pieces slide past each other. And one great example of a transform fault is this along the California coast. So these faults are vertical in nature and are produced where the stresses are exerted parallel to each other, sliding against each other. A well-known example of this type of fault is the San Andreas fault in California. Okay, we now looked at the different types of folding and different types of faulting that gives rise to the various surface features on the Earth. Now look at an example of that was the San Andreas fault, where a road got cut down due to the parallel movement. Okay, now earthquakes are quite clearly connected with all these plate tectonic. Now look at the devastations that an earthquake can create. We are familiar with this. We have seen pictures of this all over in the last few years. When the crustal plates break, the sudden movement of rocks, sudden movement of blocks of rock produces vibrations that move out as waves. We talked about these waves in the last class. Now these waves are called seismic waves. Most earthquakes occur along a fault plane, and they occur near the Earth's surface. So most of these occur along a fault plane where the rock, as a result of stresses, have been broken. Is that right? And that happens near the surface of the Earth. Now the map below shows locations of earthquake. Now this is the picture you have actually seen in the last lesson. Now these are locations of major faults where earthquakes generally occur. Now all these areas where the compressional forces or tensional forces have created faults that causes earthquakes. Geologists and geographers call the origin of the earthquake the focus. That means a place where an earthquake occurs, that is, a piece of rock shudders. It is the shuddering or the sudden movement of a piece of rock that causes the earthquake. And the place where it occurs is called the focus of the earthquake. Now remember, the focus is not on the surface. It is underneath the surface. Since this is often deep below the surface and difficult to map, the location of the earthquake is often referred to as a point directly above on the surface of the Earth. So if the focus of the earthquake is somewhere underneath the surface, a point directly above it on the surface is called the, what do you call that one? It's called the epicenter of the earthquake. So such a point is called the epicenter. When the weatherman talks about an earthquake, he always talks about the epicenter. Remember, epicenter is not where the actual earthquake occurred. The actual earthquake occurred deep underground at the focus of the fault line. Epicenter is a point directly above it on the surface. Now, if this is the focus where the earthquake has actually happened, the epicenter is above it. So, the focus is actually along the fault line. This is the fault line, and the earthquake happens along a fault line, and the epicenter is directly above it. The strength or magnitude of the shock waves determine the extent of damage caused. You know that, and the strength of an earthquake is measured in a unit called Richter scale. I will mention that as we go on. Earthquakes are three-dimensional events. What does that mean? The earthquake waves are propagated in all directions. It is not along just a plane. It goes in all directions. It's a three-dimensional event. The waves move outwards from the focus where it occurs. The waves move outwards and travel both horizontally and vertical planes. That's why I said it is a three-dimensional process. This produces three different types of waves. Remember, we talked about those three different types of waves in the last class. What are they? First are the P waves, or the primary waves, and they are identical to sound waves. We can call them longitudinal waves. They are high frequency, short wavelength, longitudinal waves which can pass through both solids and liquids. Now, the ground is forced to move back and forth. Yesterday I demonstrated that to you, that a longitudinal wave is a back and forth motion. Now let me see if I have a picture. I think I have a picture. I'll show it to you. This produces relatively small displacements on the ground. Now here is an example of a longitudinal wave. These pillars are rocked back and forth. You can see as a result the fence is broken. The back and forth motion has resulted in the stresses that created that break. So these are P waves, or longitudinal waves. And you know, P waves can travel through solids and liquids. Alright, so P waves can be reflected and refracted, and under certain circumstances can change into a second type of wave called the S wave. Alright, we will look at the next type of wave. That will be, anybody remembers the second type of wave we talked about? The rocks on the second type of earthquake waves are called the S waves. What is the difference between P waves and S waves? Well, S waves, or secondary waves, travel more slowly than P waves and arrive at any given point after the P waves. Now, like the P waves, they are high frequency, short wavelength waves, but instead of being longitudinal, they are transverse. Now, what is the difference between a longitudinal wave and a transverse wave? Let me see if I can demonstrate that to you. You got to watch very carefully, because I'm trying to do it in here and it may produce some sound. So now watch here. I have a slinky here. I hope you can see here. Now watch the longitudinal wave, or the P waves. Now the P waves are waves created by, watch this one now. Now what is happening to the segment of the slinky? The segment of the slinky are moving back and forth, producing compressions. Now this is a P wave. Now, that is a longitudinal wave. Whereas S waves are transverse waves. Now what is the difference here? Watch how that wave is going to be gone. Now that is a transverse wave. In other words, the segment of the spring moves up and down, and the wave goes at right angles. Whereas P waves, or longitudinal waves, the segment vibrate back and forth, and the wave advances in the same direction. So that is the difference between longitudinal wave and a transverse wave. So P waves are longitudinal waves and S waves are transverse wave. And the main difference between them, apart from the one I just showed you, longitudinal waves can travel through solids and liquids, whereas transverse waves can only travel through solids. So they move in all directions away from their source at speeds which depend upon the density of the rocks through which they are moving. They primarily move through rock, and they cannot move through liquids. Well, this is the illustration of that. I think you can understand. The poles are now vibrating back and this way, transverse in a right angle direction, and the wave is going that way. That is an S wave. On the surface of the earth, S waves are responsible for the sideways displacement of the walls and fences, leaving them the S-shaped, and that's why the wave is called an S wave. Well, a third type of wave are the L waves, which are actually the surface waves, are rather low frequency transverse vibrations with a very long wavelength. Now they are created close to the epicenter and can only travel through the outer part of the crust. Now these waves will not pass through the interior of the earth. The L waves can only travel through the outer crust, and they are responsible for the majority of the building damage caused by the earthquakes as they are going on the crust. Now this is because L waves has a motion similar to the waves in the sea. You see the difference there, if you can watch my pointer here. In a longitudinal wave, the particles move back and forth, or the rock is made to vibrate back and forth when the wave advances that way. In the case of an S wave or transverse wave, the rock is made to vibrate up and down and the wave advances that way. Whereas an L wave, the rock on the surface are made to vibrate in a sort of circular way, you see, and that is what causes most of the damage due to the earthquake. Now there you can see the rock on the surface are made to vibrate in a circular way, not exactly back and forth, not exactly up and down, but it's actually a combination, just like the waves in water. There is sort of a circular oscillation happens. The ground is made to move in a circular motion, causing it to rise and fall as visible waves moves across the ground. What is a tsunami? You see, when an earthquake occurs under the ocean, at the ocean bed, it creates great big waves which then travel at a very fast rate towards the shore. Now what happens is, at the beginning, because of the shock of the wave, the water is pulled towards that disturbance. That means on the shore, the water recedes. Now if you remember, at the time of the tsunami in the year 2000 in Indonesia, the local people, the native people, saw that the water recede a very long way out, which is not very common. And immediately they understood, even the animals understood, that this water has been drawn by an earthquake. That means this water is going to return furiously. So, where the earthquake occurs, initially the water gets sucked in, and the great explosion there creates the great wave, which then will advance to the shore with a great speed. Tsunami is a Japanese term to describe the very large ocean waves generated by earthquakes, landslides, or such similar occurrences. Common ocean waves produced by winds travel at speeds of about 90 kilometers per hour. Now, in one of the lessons that we will be doing in the next section, we will talk about the waves created on the ocean by wind. Now, those waves are normal waves. They travel about 90 kilometers per hour, very fast though. But these tsunami waves, they travel much faster than that. Now here's a tsunami wave. Now tsunami is produced by strong disturbance in the floor sea, and they travel at speeds of 725 kilometers per hour and produce waves as high as 8 meters high. So that means it is going to be creating a great big flood when it comes ashore. Now, because tsunamis have very long wavelengths, They come ashore more like a long-lasting flood. You don't see the waves coming. We see the water simply rising. Why? Because tsunami waves are very long waves. You see water simply rising, and they come up very fast because these waves move at over 700 kilometers an hour. Now here they come and break on the shore and flood the shore so rapidly that you will have no time to escape. So that's the reason why the local people, when they saw the water receding, they want everybody around say, let's escape. So those who went away that time escaped. But when it begins to come back, it comes very fast. You will have no time to run. You cannot run at a speed of 795 kilometers per hour, can you? No, that will overtake you. Now the strength of an earthquake is defined using the Richter scale. Now this is Dr. Richter, who's been working with his seismograph. This is Charles Richter studying a seismogram. The magnitude on this scale is a measure of the strength of an earthquake or strain energy released by the earthquake as determined by the seismographic observations. And what kind of Richter scales are possible? Have you heard about the normal strengths of earthquake? In the last 5 years, we heard of earthquakes, a great big earthquake in Pakistan, an earthquake in Japan, and several earthquakes in Indonesia, a small earthquake in California. You remember what kind of scale and what kind of destruction these earthquakes can bring about? Well, I have the magnitudes are measured of magnitude 8, magnitude 7, 6, 5, 4, and so on. Now, on an average, we get about 2 earthquakes that are on magnitude 8 a year. And fortunately, most of these earthquakes occur under the sea, and we will not notice it. Now, magnitude 8 is a great earthquake, and that if it happens on the land, it will cause total destruction. So, there's about 2 of them in a year. 7 is a major earthquake. It will cause extensive damage, and on an average, you get 20 of them a year. Strong earthquake of magnitude 6. Most of the earthquakes that we hear are between 6 and 7, 5 and 6. So magnitude 6 is a very strong quake with some destruction. And there are approximately 100 of them a year. Magnitude 5 is moderate quake with structural damage. Now, if you notice that when the earthquake occurred in Pakistan, which was, I believe, a 6.8 earthquake. You see, it was very close to being 7. That means it was a major quake, causes extensive damage. The same earthquake that occurs in California, the same strength, will not cause even 10% of that damage. Why? I have told you in the beginning of the lesson that when we know about the nature's behavior, we can prepare for it. Most of our cities that are prone to these natural disasters are ready for it. Well, we were not ready for Katrina, were we? Well, we know the levee was not good enough. Now, when we know things like this happen, we now prepare ourselves. So I hope next time something like that comes to New Orleans, they will be ready. The levees will be ready to hold, and they will be spared of such disasters. Well, magnitude 4 is a minor quake with local damages. There are about 15,000 of those a year. And magnitude 3, a rather small quake with fairly no damage. you experience a little shake, and that's it. And there are over 100,000 of those. That means earthquake is a common phenomenon. It practically occurs every time. We don't know it. Very often we don't hear about it. Now, these plates where there are faults are very often creaking and moving. They are fidgeting. They are very uneasy. And that gives rise to earthquake, the shock waves, and so on. So, we talked about the forces that shape the surface of the earth. Is that right? Diastrophism, volcanism, and earthquake. That was the main topic of today's lesson. And these are the forces that actually shape the surface of the earth. There are other forces. We talked about erosion. We will talk more about those in our next lesson. And I will see you for the next lesson later on.